Hello, it's Dr. Daystorms, and today's video is on what happens when you have more than one possible Lewis structure. You know, which is correct, are they equal, and what does it really look like for this molecule? And so this actually comes from this term, or the term is called resonance structures. So first of all, let's look at ozone, and in case you didn't know, ozone is O3. Okay, so let's look and see what its resonance, or what its Lewis structure would look like. And so if you draw the ozone, and once again I can't stress this enough, but whenever you start doing these Lewis structures, you want to make sure that you always start putting in the formal charges. And see, if you notice, this middle oxygen actually has a formal charge of +1. That's because oxygen has 6 valence electrons, but this oxygen owns 1, 2, 3, 4, 5 electrons around it. So 6 minus 5 is a +1, which many times they just put as a plus sign. Likewise, this oxygen that we have drawn on the left, it actually has it had 6 valence electrons, but currently it has 6 lone electrons plus 1 bond, which means 7. So it's a -1 charge. But the oxygen on the right, it's neutral because it has 4 lone electrons and 2 bonds. So therefore it'd be 6 minus 6, which is 0. So that's a possible Lewis structure. However, this is also a possible Lewis structure. Let me draw it. What about this one? We have the middle oxygen, but we have the single bond on the oxygen that's on the left. So it's now negatively charged. And the double bond is on the oxygen on the right. Now, one interesting thing about double bonds and single bonds is a double bond is shorter than a single bond, so single bonds are longer. So which of these two resonance structures, two possible Lewis structures, is correct? And actually what happens is you can take an X-ray. There's something called X-ray crystallography. And you can take an X-ray of this, essentially. And what they notice is neither one is correct. Because the true observed structure here shows that the two bond lengths are identical. And if you look at the electron density, this is like a hyper-colored map. The red areas show you where it's there are more electrons versus the blue area where there's less electrons. And if you figure up the charge, each oxygen, instead of being -1/2, each oxygen on the outside, these outer oxygens, have a charge of -1. I mean, instead of one of the oxygens having a charge of -1, each oxygen on the outside actually has a charge of -1/2. So they're actually being shared between the two. So we call these resonance structures. These two structures that we drew before are actually equal. Okay, so since the one Lewis structure doesn't accurately depict what happens, where it would have, one short bond and one long bond and one short bond, in reality they're two bonds of equal lengths. Sort of, instead of being a double bond, it's 1.5 bond. You have to mix, or you blend the two in together. Okay, so we use multiple structures called resonance structures to do this. Many times the way that we draw this would look like so. Here, let me show you. Let me get a different color though. We put a bracket and you draw both possible structures. Always put your charges in. Just always get in the habit of putting charges in. And we put this little arrow here. It's a double-sided arrow. Let me draw the second one. Neither one of these is 100% correct. That's why we put the brackets around it and show the double-sided arrow, because it's really a blending of the two. So what do I mean by that? So just like if you consider the color green, Green is what happens when you have like the color blue and the color yellow, the primary colors, you mix them together and you get green. Ozone, the actual structure of ozone, really is a blending of these two structures. And so we get that instead of having a double bond and a single bond, you have two oxygens connected to the central oxygen by a 1.5 bond. Okay? So let's look at another example. Let me change the color once again. So let's look at formic acid. This is a possible Lewis structure of formic acid. Okay. Now you do the formal charges. When you figure out the formal charges, you'd see that this oxygen that I have drawn on the right-hand side would have a -1 charge. However, there's another possibility. So we would want to do this as a resonance structure. That possibility is where, let's suppose that we convert 2 of the electrons here to a double bond, and we break one of these bonds to make it a single bond. So essentially, what would happen is this is the second possible Lewis structure, where the single bond is to the oxygen at the top. And now it's the negatively charged one. And this oxygen has the double bond. So these are resonance structures. Neither one is 100% correct, and the actual structure is where the electron density is being shared between those two oxygens. It's just we can't accurately draw it, so we draw these resonance structures. Okay? So to summarize, the truth is that the electrons that form the second CO bond and double bonds below don't always stay between that carbon and the oxygen, but they move freely. And the term for this is really important. They are not localized. Instead, they use this term called delocalization. Okay? Perhaps one of the most common structures is benzene. Okay, benzene is C6H6. So if we draw benzene, you'd have 1, 2, 3, 4, 5, 6, H, 5, 6. Double bond, single bond, double bond, single bond, and a double bond, and a single bond. That's one possible structure, but we could also have a second possible structure where, and I'll change it and put it in a different color. It looks like this. Okay. These are the two possible resonance structures. So many times they put brackets around them to show that they're introverted. And in reality, what happens is the electrons are free floating, or they're delocalized, and they form a ring. Same thing here. They're going between they're shared amongst all of the carbons. So another way that they often show this with benzene is, and it's actually a really good representation of it, looks like follows. So many times what they like to do is they draw it this way. Oh, here, I want to try to keep the color scheme the same as I did before. Okay, and since the electrons are delocalized, that's the same thing as saying this. And they like to draw benzene, just like yellow and blue make green. Here I'm showing that the yellow structure and the blue structure go on to make this green structure. and they draw it sort of like a hex nut, because these electrons here really are delocalized. And that's what benzene would look like. You should just practice as many examples as you can of drawing different resonance structures until you get more comfortable with drawing them. And if you have any questions or problems, please feel free to come to me during office hours, during our study sessions, and we'll have another study group session next Tuesday just before our exam on Wednesday. This slide here just shows the same thing that I drew. It's just prettier. And so I will see you in class. Take care.